All right, 1423. So first I'm going to draw my picture. So here's my picture, and I have a box. It's being pulled with a force. So a push or a pull is a applied force. And remember, the direction of the vector, the force vector, is important. And this is acting at an angle of 30 degrees. And the mass is equal to 5 kilograms. Now, when you read problems, you have to be really careful because there's other information in the problem that means something. So in my given, they ended up telling me that it starts from rest, which means the initial velocity is 0. The first thing I'm going to do is I'm going to draw my free body diagram. On the AP test, this is where people make a mistake. You never, ever draw components on your free body diagram. They only want you showing forces in the direction in which they act for the free body diagram. Now later on you're going to break it up into components, and breaking it up into components is what you're going to do to solve the problem. So what I'm going to do first is I'm going to draw all the forces acting on it. So I'm going to draw my box. So first of all, because it's a mass, it's going to have a weight acting down. So that's F of G. Now I always have to establish my sign convention. Because this box is moving to the right, I'm actually going to write here moving. Why am I bothering to write that? Because I'm then going to say my sign convention is up and to the right is positive. So you want the positive direction to be in the direction in which the object is moving. So it's not going to hurt me to write that down. Now, this is a contact force here. The weight is pushing down. The normal force is going to push up. Now remember, when you think about the normal force, you need to think about the normal force is always going to be perpendicular to the surfaces in contact. Okay? Don't think up, think perpendicular to the surfaces in contact. All right, and then I have my 10 Newton applied force here. So those are all the forces acting on the object. If this was an FRQ, first of all, I would draw my normal force going to the ground. And then my weight would be from here, and then my applied force would probably be at the edge, if they say at point of contact. Okay? So that's what I would do for my free body diagram. But in order to solve this problem, I want to show all the forces acting either perpendicular or parallel to the surfaces in contact. So my weight is perpendicular, so that's good. My normal force is perpendicular, but the applied force is acting at an angle. So what I'm going to do is I'm going to do it to the side so I don't make a mistake. So this is going to be 10 newtons, and I know that this is 30 degrees, so I'm going to draw the components. This is where I start. So from where I start, I'm going to go horizontal. And you notice I put an arrow there. I need to show the direction on my components. If I don't, especially when we get to things much, much more complicated, it's not going to work out. From the head of this vector, I do the tail of the other. So again, there's my direction. So this is FAX, and this is FAY. So FAX is adjacent to the given angle, so it's FA cosine of 30 degrees. So FAX is equal to 10 cosine of 30 degrees, and this comes out to be 8.66 newtons. FAY is equal to 10 sine of 30, and this comes out to be 5 newtons. So now on this diagram, instead of FA acting at an angle, I'm going to now have FAX, and then I'm going to have FAY. So I just drew the FAY to the side like this. Now, once I do this, I'm home free. Because now all I'm doing is I'm summing my forces. So right off the bat, before I start, I can just say F of G is equal to mg, and that's equal to 5 kilograms times 9.8 meters per second squared, which is equal to 49 newtons. So where do I start? It doesn't matter. I'll sum forces vertically. So I'm going to say the summation of F of y is equal to ma. Now, is this block accelerating in the vertical direction? No. It's not even moving in the vertical direction. So this is 0. So you have to write as 0. Now again, I go up and to the right because if the acceleration is 0, the whole term is 0. Now underneath, I'm going to look at my free body diagram, this one right here that has the components, and I'm going to say what's positive and negative. So up is positive, Fn is positive, Fay is positive, minus f of g is equal to 0. Now I'm going to rearrange the equation to solve for the unknown in terms of the known. So Fn is equal to f of g minus Fay. Now I'll substitute in my values, 49 newtons minus 5 newtons. So Fn is equal to 44 newtons. Step by step, no shortcuts. Now I'll sum forces horizontally. So again, I look at this picture. Summation of f of x is equal to ma. Now, is this block accelerating in this direction? Yes, because if we read the problem that says find the acceleration of the mass. So this is not 0. So now when I look at my diagram here, I only have one force. So Fax is equal to ma. So I'm going to rearrange the equation and say Fax over m is equal to a. So that's 8.66 newtons, which is a kilogram meter per second squared, divided by 5 kilograms. So remember, if this is a kilogram meter per second squared, the kilograms cancel and only end up with meters per second squared, which is the correct unit for acceleration. That's why in physics, we have a foolproof way to check our work every time. We carry our units through and cancel them. So this came out to be 1.73 meters per second squared. Then it said, so we found the normal force. Oh, how fast has the car moved in 6 seconds? Okay, so what do we know now? We know the time is 6 seconds. We just found out the acceleration was 1.73 meters per second squared. We know it started from rest, so V naught is 0, and now we want to find x. So now we're going to say to ourselves, okay, which equation has T, A, V naught, and x? And that's going to tell me what to do. So the equation is x is equal to V naught T plus 1/2 AT squared. V naught is 0, so that whole term goes to 0. So x is equal to 1/2 1.73 meters per second squared times 6.2 seconds squared. So x comes out 33.25, which we'll say is 33.3 meters. The more you write down on paper, the less likely you are you make a mistake. So even in this case, that's why it's important to write our given. When I'm not sure what to do, I want to find x, I have T, A, and V naught, the problem kind of solves itself. It's a systematic approach to solving a problem. And a lot of people are, so you write it all down.